Hey everyone! Today we are going to follow one of the most incredible stories our planet has to tell, the epic journey of magma. We're going to see how it's born deep inside the Earth, how it travels, how it changes, and ultimately how it literally builds the very ground beneath our feet. So let's start right at the surface with a really simple question. When you see a new volcanic island pop up in the ocean, or you look at a massive mountain range, where does all that stuff actually come from? Well, the answer isn't on the surface. To find it, we've got to travel hundreds of kilometers straight down. So here's the game plan. We're taking this journey in 5 stages. We'll start in the planet's engine room, figure out how you even melt solid rock, watch the magma change as it rises, see its big finale, and then check out the amazing legacy it leaves behind. Okay, let's dive in. Our story begins deep inside Earth's fiery heart. We're going way, way down into the upper mantle, which is where all magma gets its start. Now, the very first thing we need to get straight is a pretty huge surprise, one that completely busts a common myth. We all kind of picture the mantle as this giant ocean of lava, right? But it's not. It's actually a layer of incredibly hot but solid rock that's kept from melting by just immense pressure. And let's meet the star of our show. The rock itself is called peridotite. It's this dense, dark rock packed with iron and magnesium. You can think of this as the parent material, the raw ingredient that's going to eventually transform into magma. Which, of course, leads to a pretty big question. If the mantle is solid, how on earth does it ever melt and create magma in the first place? And that is the perfect lead-in to our second section, how to melt a rock. And as you're about to see, it's a lot more complicated than just cranking up the thermostat. So it turns out there are 3 main ways to get that solid peridotite to melt. Yeah, you can heat it up. That's the obvious one. You can also add things called volatiles, like water, which basically lowers the rock's melting point, kind of like how salt melts ice. But the really big one is decreasing the pressure. It's like a pressure cooker. If you suddenly rip the lid off, all that superheated water inside instantly flashes to steam. The exact same thing happens to rock. And this idea of decompression melting is so important. When that mantle rock rises up fast, say at a mid-ocean ridge where tectonic plates are pulling apart, the pressure drops way faster than the rock can cool off. So it crosses its melting point, and just like that, magma is born. This one single process is responsible for creating basically all of our planet's ocean floor. Okay, so we did it. We've got magma. But its journey is just getting started. And like any great traveler, it's going to be changed by the journey it takes. The key process here has a fancy name, fractional crystallization. Basically, as the magma rises and starts to cool, different types of minerals start to crystallize out of it at different temperatures. The heavier, iron-rich minerals usually form first and then sink. You can think of it like a geological refinery that's constantly separating out ingredients and changing the recipe of the liquid that's left over. And here's the perfect before and after. The original parent magma is super hot, really runny, and full of magnesium and iron. But after fractional crystallization does its thing, the evolved magma that's left over is cooler, way thicker, almost like honey, and much richer in silica. And trust me, this change is absolutely critical for what's about to happen next. This change in chemistry brings us right to the climax of the magma's journey. When it finally reaches the crust, it faces a choice between 2 very, very different endings. Now, here's a wild fact about volcanoes. We think of magma, and we immediately think of eruptions, right? But the vast, vast majority of magma never actually reaches the surface. It gets trapped inside the crust, where it just sits and slowly cools down and solidifies over millions of years. But that small fraction that does make it to the surface, it puts on a show. Remember that thick, silica-rich magma? Well, that thick, sticky stuff is amazing at trapping gas, almost like a cork in a champagne bottle. So when the pressure is finally released, boom! You get explosive eruptions, creating these fine-grained volcanic rocks and incredibly dramatic things like pyroclastic flows. But the much more common story is the intrusive one. This is where the magma cools down incredibly slowly, sometimes taking millions of years. This gives plenty of time for large, beautiful crystals to grow, forming coarse-grained rocks like granite. These huge underground bodies of rock, called plutons, are massive. They form the very core of entire mountain ranges. So, what's the final legacy of this whole journey? Well, let's take a look in our final section, a rock's rocky legacy. What's so cool is that how it cooled leaves a permanent signature on the rock. If it cooled slowly, deep underground, you get a phaineritic texture with big crystals you can easily see, like in granite. If it cooled super fast on the surface, you get an aphanitic texture, with crystals so tiny you need a microscope. A geologist can just look at a rock's texture and basically read its entire life story. And this whole process gives us this incredible diversity of igneous rocks. You get the basalt that makes up the ocean floor, the granite that builds our continents, and the andesites and rhyolites that create volcanic mountains. They're all children of magma, just shaped by totally different journeys. So, what's the big takeaway here? It's this absolutely staggering number. More than 90% of the Earth's crust is made of igneous rock. That means almost everything. The land we live on, the mountains we climb, the floors of the oceans, all of it began as molten rock on this incredible journey. It really is the fundamental story of how our planet was built. This constant cycle of melting, rising, changing, and finally solidifying is what has shaped our world for billions of years, and it's still happening right now. Which really just leaves us with one last thought. After seeing the immense pressures, the incredible heat, and the millions of years it takes to create these basic building blocks of our world, should we ever take them for granted? Thanks so much for watching.